Guys, the last gas law. The last gas law is, here's my pen, Dalton's law of partial pressure. It's the easiest of all the gas laws. So basically it says that if you have a container and you have a mixture of different gases in that container, they're all going to have the same volume, right? And each one of them could have a different pressure. So the total pressure of the whole mixture of gases, all you have to do is just add up all the individual pressures of the specific gases. And why do they have different pressures? They're probably different number of moles. So if they have the exact same number of moles, each different gas, each one is going to have the same pressure. But if they have different amounts, each is going to have a different pressure. They're all in the same volume. Long story short, this is Dalton's law of partial pressure. This says the total pressure exerted by a mixture of gases is the sum of the partial pressures of the individual gases present. Now, I know it doesn't say anything about moles in this, but you just have to understand that if you have two gases and they have the exact same pressure in a container, they are the same number of moles, okay? Because when you think of the PV equals nRT, if the volume of this is the same and the temperature is the same, if the moles are the same, then obviously the pressures will be the same, okay? Anyway, so this in a nutshell is what the equation looks like. Total pressure is equal to pressure of A plus pressure of B plus pressure of C. So if you have a container and there are three different gases, in order to get the pressure of the whole container, all you have to do is add up the pressure of the individual gases. So let's say you have the pressure of oxygen is 2 atmospheres. And you have the pressure of hydrogen is 2 atmospheres. And maybe the pressure of nitrogen is 1 atmosphere. Okay, so we have the same number of moles of oxygen and hydrogen. This is 2 atmosphere, this is 2 atmosphere, and this is 1 atmosphere. All right, so what would the total pressure in the container be? You would write 2 plus 2 plus 1. You end up with 5 atmospheres. It's as simple as that. If you are given the total pressure and you're given a couple of the gases and one is left out. So let's say you have this scenario here. You are given that the total pressure in the container is, let's say, 3 atmospheres. That's your total pressure. And you know that you have carbon dioxide, nitrogen, helium, in the container. And you know that the carbon dioxide is 1 atmosphere, and maybe you know that the nitrogen is 0.5 atmospheres, and they tell you, well, what is the pressure of the helium? So you go total pressure is equal to pressure of CO2 plus pressure of nitrogen plus pressure of helium. Okay, so you know that the pressure of the carbon dioxide is 1 atmosphere. The pressure of the nitrogen is 0.5 atmospheres. These are your adding. And then the pressure of the helium, that's your unknown. Pressure of the helium is the unknown. Total pressure is 3 atmospheres. Seems really easy, right? And it is really easy. This minus this minus this. Pressure of helium is 1.50 atmospheres. Okay, that's Dalton's law of partial pressure. But I wanted to add in that concept of equimolar means equal pressure. So if they have the same number of moles, they're going to have the same pressure, the individual gases. Okay, so we're ready to move on to the next topic on our what you need to know list. And that topic is phase changes or change of state. It's something we talked about in a previous chapter, but we're just addressing it again in this chapter because this chapter deals with solids, liquids, and gases. So let's go ahead and say solid, liquid, gas. Okay, so if you are going to go from a solid to a liquid, you're melting. If you're going to go from a liquid to a gas, this is evaporation. The boiling point is when the vapor pressure is equal to atmospheric pressure. We're going to talk about that. But in order to do this, to go from solid to liquid or liquid to gas, you have to put heat in. So whenever you're adding heat, this is called endothermic process. So an endothermic process is just a process where you're adding heat in. Okay, endothermic, heat is going in. To skip the liquid phase entirely and go from a solid directly to a gas, if you remember we talked about that in a previous chapter, I think it was the first chapter, that is sublimation. Sublimation is also an endothermic process where you're putting heat in so you can go from a solid directly to the gas and bypassing the liquid state. All right, what about the reverse? To go from a gas to a liquid, that's called condensation. Liquid to a solid, that's called freezing. And then gas all the way down to a solid, that's called deposition, bypassing the liquid phase. All of these processes, condensation, freezing, and deposition, you have to take heat away. Take heat away, and this will happen. These processes are called exothermic processes. Okay, so those are your 6 movements from one phase to another, one state of matter to another, and you should know the terminology exothermic and endothermic. All right, the next step deals with a little bit more on liquids rather than gases, but a little bit of gases. It's a term that we haven't seen before, and that is vapor pressure. So anytime you have a liquid, the molecules of liquid that are right on the surface of the liquid sometimes have enough energy to escape and become a vapor. The pressure exerted by that vapor, that's called the vapor pressure. So let me give you a textbook definition of vapor pressure. I'll just get it straight from here. And if I can find it, yep. Oh, they have definitions of what a vapor is. A vapor is just the gas over a liquid. Okay, so vapor pressure is the pressure exerted by a vapor above, which is what I just told you, above a liquid. When, and this is the part I should mention, when the liquid and vapor are in equilibrium. What does equilibrium mean? It means that, okay, so you have this container and it's got a liquid in it. So this is a liquid. Now let's cover the container. These molecules right on the top here, they escape and they become a vapor. And some of the vapor comes back down and becomes a liquid. Equilibrium means that the rate of the liquid becoming a gas and the gas becoming a liquid is equal. All right. So the pressure of whatever gas droplets are above the liquid, that's what vapor pressure is. Why is this important? Because the textbook definition of boiling point has to do with vapor pressure. So let me go ahead and give you that definition and give you the definition of a volatile liquid. The term volatile, a volatile liquid, is a liquid that easily evaporates. easily evaporates. So if you've got a liquid that will easily evaporate, it's called a volatile liquid. If you have a liquid that doesn't easily evaporate, it's called a non-volatile liquid. Okay, boiling point of a liquid occurs when the vapor pressure above a liquid equals atmospheric pressure. This is pretty interesting because as you increase the temperature, the vapor pressure goes up. So put in your notes, as you increase the temperature, the vapor pressure goes up. So as you're heating up this liquid, you're getting more vapor. You have more vapor, you have more pressure. So as you increase the temperature, the vapor pressure goes up. And it keeps going up, going up, going up. When the vapor pressure equals the atmospheric pressure, so think about this. The atmosphere is pushing down on this. The vapor is pushing up. When the vapor pressure equals the atmospheric pressure, then the liquid is going to boil. And the temperature at which it boils, that's called the boiling point. All right, we'll do some practical applications of this in the next video, and then we'll move on to the last key topic, which is intermolecular forces.